In this tutorial, we will learn how to define and apply controls in VOLTRA. We use another file than previous tutorials. If necessary, you can download the project files for this session from the link provided in the comments. For more detailed theoretical background, please refer to section B.20 of the VOLTRA manual, where the control functionality is explained in depth. In this example, we simulate an electric floor heating system. The electric heating cables are assumed to be placed on top of the insulation layer. Therefore, heat is transferred from the insulation, defined with color 135, to the screed, defined with color 120. In VOLTRA, this heat transfer is modeled using a border face boundary condition. Two heat flux functions are defined for this boundary condition. One function represents 100 watts per square meter, corresponding to the heating being on. The other function represents 0 watts per square meter, corresponding to the heating being off. The switching between these two functions is managed by the control system. Initially, the off condition function I01 is assigned in the border face BC window so that the heating is inactive at the start of the simulation. To define the control, click on the controls icon in the top toolbar or open it through Edit and then Controls. In the Controls window, click Insert After to add a new control row. The control requires several parameters to be defined. The first parameter is the sensor node. This must be an output node. At each time step, the control compares the temperature at the sensor node with the defined target temperature and decides whether to switch the heating on or off. In this example, we want to compare the room temperature with a target value. Within the room, here modeled as a BC-free-S, a small block is placed to act as a temperature sensor. An output node is defined within this block in order to obtain the temperature value. Next, we define theta target, which is the target temperature. This must be defined as a function whose reference starts with the letter T. Any type of function can be used. Even if the target temperature is constant, it still needs to be defined as a function, which is what we have done in this example. The sensitivity upwards and sensitivity downwards define the hysteresis range of the control. For example, if the target temperature is set to 20 degrees Celsius and both sensitivities are defined as 0.5 degree, the control will switch on when the temperature drops below 19.5 degrees and switch off when the temperature rises above 20.5 degrees for heating purpose. This hysteresis prevents frequent switching and ensures stable operation. The purpose of the control can be set to either heating or cooling. In this case, heating is selected. When the sensor node temperature drops below the target temperature minus the downward sensitivity, the control switches on, which means switching from the off function to the on function. When the sensor node temperature rises above the target temperature plus the upward sensitivity, the control switches back off, meaning here from the on function to the off function. For cooling applications, the logic operates in the opposite manner. The time off and time on parameters are not defined in this example. If these values are specified, they introduce minimum durations for the on and off states. In that case, even if the temperature crosses the switching thresholds, the control state will not change until the defined minimum time has elapsed. In this example, functions I01 and I02 are used. However, any function type available in the status bar can also be applied here, depending on the specific control strategy you want to implement. To monitor the control behavior, open the report definition and add the control action as well as the sensor node temperature to the output. The control action will have a value of 1 when the heating is on and 0 when it is off. Now click Calculation to run the simulation. After the calculation is complete, open the text output and report output to review the results. You will observe that when the temperature drops below 19.5 degrees, which corresponds to the target temperature minus the downward sensitivity, the control is activated in the next time step. The heating turns on and the temperature starts to rise. When the temperature exceeds 20.5 degrees, which corresponds to the target temperature plus the upward sensitivity, the control switches off. Due to the thermal inertia of the floor, the sensor node temperature continues to rise for a short time even after the heating has been turned off. After reviewing the results, close the output window and return to the controls dialog. You will notice that additional parameters can be defined in the controls window. These are related to ventilation flow control. We will now close this exercise and proceed to the second one to go over these parameters. In this example, the facade is ventilated, and the ventilation rate is controlled based on two criteria: the sensor temperature at the wall side and the temperature difference between the outdoor air and the cavity. When the selected function from and function to are ventilation functions, VOLTRA provides additional control options. One of these options allows you to test the temperature difference between two zones. To use this feature, activate the Test Delta Theta option. In this case, we compare the outdoor zone, defined with color 2, and the cavity mean temperature, defined with color 246. A minimum temperature difference of 5 degrees is required to activate the control. Both of these zones must already be defined in the ventilation path. Since the purpose of the control is cooling, the outdoor temperature, which is zone color 2, must be at least 5 degrees lower than the cavity mean temperature, zone color 246, for the control action to be enabled. For heating applications, the logic works in the opposite direction. In the report definition, we include the sensor node temperature, the outdoor temperature, the mean cavity temperature, and the control action. After defining these outputs, click Calculation to run the simulation. Once the calculation is complete, open the text output and then the report output to evaluate the results. As you can see, even when the sensor temperature exceeds the target temperature of 20 degrees, the control action is not activated if the temperature difference between the outdoor zone and the cavity is less than 5 degrees. Only when the temperature difference exceeds 5 degrees does the control become active, and this change takes effect in the following time step. Thank you for watching. See you in the next tutorial.